Hi, I'm Peyton Kilborn, and this is my lab report for our first lab regarding constant velocity motion. For an introduction, the purpose of this lab was to use the momentum principle and an experiment to understand the motion of an object that is moving at a constant velocity. And some of the key ideas were that the object, in my case a pass car, is moving at a constant velocity, and that using the momentum principle, the second key idea is using a momentum principle to predict the motion when there is no outside unbalanced force. And the third key idea is a comparison between the observed position from tracker and the predicted position from our glow script model. And the overall results from this lab, the comparison, is that the expected and actual results varied only slightly, but we'll get into that more later when we're analyzing the graphs. Here are our two relevant equations. On the top, we have the final velocity equals the initial velocity plus the net force divided by the object's mass times the change in time. But in our case, we're assuming that the net force is 0, so that the final velocity is the same as the initial velocity. And then in this, we have the final position equals the initial position plus the average velocity times the change in time. We use both of these a lot throughout the equation, throughout the lab. And then here, I'll take the chance to go over some assumptions that we made throughout our lab. The first one was that assuming there would be no outside forces, so the net force would be 0, and that the object is going at a constant velocity. And both of these are that we can use the momentum principle to judge our data. Here is the video of my object in tracker. Here is the system. It is just the pass car. The surroundings would be basically anything else. And just some details for the experiment. They are that in this experiment, I pushed the car in the track, left it to go at a constant speed, recorded it, used that in tracker to determine the position, which are all those red dots. And then from there, I took that over to GlowScript to get the computer model of the expected positions. Here are the initial positions. The mass I found online. This ends up canceling out later, so it's not 100% important. Here's the vector for the object's initial position, the vector for its initial velocity. Here's the initial time. It was set that way so that it wouldn't have any interference with the object speeding up. Here is the change in time. It aligned with frame rate. And then here is my code. That was the end time. Here we have the vector for force being 0. Here are those two equations from before, just rewritten with the variables that the computer would understand. And again, this F net divided by the mass times delta T would come out to be 0, leading to constant velocity. And then here is the link to my GlowScript code. Here are the graphs. On the left side, that's a graph of velocity versus time, showing a constant velocity. And on the right, that is the two difference in positions. The red, the upper one, is from the model. The blue lower one is the position from tracker. And they both have upwards linear, positive linear relations, showing that there's the same relation of change in position over change in time. So the same relation of velocity in this, just at different slopes. So it would be obviously having found out them to be different velocities, which could have come from a few error sources, such as there being some outside forces like friction or air resistance in the experiment that prevented it from acting like the model, or that the math I used for the model for the initial conditions were used from data from tracker that could have been not the true average, leading to slightly thrown off results. And so for the initial understanding questions, what would be different if I labeled the axes differently? Nothing would change with the magnitude, with the relationship between these two. So the magnitude of the slope, the velocity would stay the same. It would just be negative. So it would start top left and end bottom right. They would have the same relationship of change in position over change in time. And then for the what does it mean? This experiment, we assumed that net force would be zero. Is it possible to determine what individual forces were added together to get the net force? I'd said it would be difficult to impossible to determine the all the individual forces because there are just so many unknown. But because the observed is slightly lower than expected, we can assume there's some slight force against the direction of the motion that caused this discrepancy in our data. And thank you for your time.